Let's start off with a game I like to call Find the Object. Look at this picture. Can you spot the piggy bank? The balloon? Pretty easy, right? This recognition comes pretty easy to most of us, since it's been something that we've been doing since we've been born. Although this is easy for us, the same logic doesn't always apply to computers. Instead of quickly analyzing a picture to find the object, computers have to use a lot of brute force to perform object detection. First, computers have to convert the image into a series of pixel numbers that they can then find patterns within. Even with the amazing computing power we have today, these computers will likely still have lower accuracy than even a 5-year-old can in recognizing objects. The main issue lies in the fact that humans can easily generalize from an image, while computers have to make patterns off of large numbers of pixels. Now, let's just think about what computers can do if they have high object detection rates. The applications are literally endless. Drones can scan an entire agricultural farm and search for weeds, boosting farm output. Machines can find faulty objects in manufacturing plants so that no faulty product ever comes to your doorstep. Lastly, they can identify malicious weapons on a person's body in airport security. Before, this was simply not possible in computers because of slow object detection times and low detection rates. How did we get from this low object detection to high object detection in computers? Enter Haar Cascades, one of the machine learning approaches that has allowed for rapid object identification and high accuracy. Haar Cascades are able to fix this problem of object recognition inside of computers, even with large input spaces that we have today. Haar Cascades consists of 4 major components: Haar features, integral images, ADA boost, and cascading classifiers. Haar features are essentially just calculations that are performed on rectangular regions inside of a detection window. This calculation involves a summation of various pixel intensities inside of this rectangular region, as shown over here. The black regions denote what is being summed, while the gray regions are what is ignored in the calculations. Although this does provide a lot of relevant data, a major problem with these Haar features is that these features can be very difficult to calculate for large images, which basically just circles back to the problem of large input sizes. Integral images can fix this by reducing calculation size and using array references rather than individual pixels to calculate the Haar features upon. This helps reduce the computational power and runtime of the model. After doing this, the model now can classify whether or not the rectangular region has an object within it. ADA boosting helps do this by using a combination of weak classifiers that each vote on whether or not the specific rectangular region has an object within it. In the ending, these classifiers help create a strong classifier that the object can now use for object detection. Now, you might be wondering, how do we create these weak classifiers? These weak classifiers are created by performing simple Haar feature and integral image calculations, and then optimizing a bounding line to separate objects from non-objects. Each of these classifiers is initialized with different weights, which helps produce different ending bounding lines, and the sum total of all these bounding lines is shown in the strong classifier and helps produce a really accurate depiction of where the object is located if it is within the rectangular region. Lastly, we can now iterate over all these steps over the entire image using cascading classifiers. Data is first passed into the algorithm and then split up into rectangular regions to calculate the Haar features and integral images upon. Then they are passed into the weak classifiers, which can detect whether an object is present in the region. And lastly, a strong classifier is created. Then, the strong classifiers are created over rectangular regions that encompass the entire image. And the final result is a bounding box for where the object should be within this image. Although Haar cascades are very useful for detection, they require a lot of variation between objects and non-objects to be accurate. Because Haar features rely on the summation of various pixel intensities, if these pixels are similar to each other, then the weak classifier cannot differentiate between objects and non-objects. One example of this disadvantage can be seen in brain tumors, where there is little variation between the brain material and the tumor. However, even with this problem of variability, Haar cascades are still incredibly powerful. Applications range from autonomous vehicles, to agriculture, to facial recognition, to robotics. The applications for this technology are enormous, and can likely be utilized in any field you can think of. So next time you end up playing Find the Object, make sure to get your computer along. The results may surprise you.